OK, so the recording is started. All right. So, bonjour tout le monde. Ce matin, nous recevons avec enthousiasme Tom Bromley de chez Xanadu. Il va nous faire un séminaire sur l'apprentissage automatique quantique dans leur boîte. Puis, puisque son séminaire sera en anglais, je vais maintenant continuer son introduction en anglais. Donc, all right. Hi, hello everyone. This morning, we host Tom Bromley from Xanadu for a seminar on quantum machine learning. Tom did his PhD at the University of Nottingham in quantum information theory, and then he moved to Xanadu. He now works as a theoretical physicist in their quantum machine learning team, and today he will introduce Xanadu's work in this field for us. All right, so welcome, Tom, and thanks for being with us today. Very appreciated, so the floor is yours.
Thank you very much. Thank you for inviting me. Yeah, it's a pleasure to be here. We're talking about quantum machine learning with Penny Lane. Feel free to butt in at any time and ask a question. I'm happy to discuss. It doesn't all have to wait until the end. So also let me know if my phone says I'm giving a poor quality connection. So let me know if I'm not coming across well at any point. Okay, so great. So the contents of this talk, it's really looking at quantum machine learning. We start off with a bit of a look at just standard machine learning, then compare that to, let me turn on the pointer. So I think you can see this now. So we look at a bit of standard machine learning, compare that to QML, then build up some of the blocks that we need to understand quantum machine learning, like how we differentiate a circuit, how we might think about constructing circuits, training and hybrid models, for example. And then I finally talk a little bit about Penny Lane and how this all fits into Penny Lane, which is our software library at Xanadu. So I did want to talk a bit more about this, but I realized that within the time frame, I'm not actually going to spend too long on this. Okay. So first, let's have a think about machine learning and deep learning. Well, I'm sure some of you have already picked up ideas about machine learning, but just from a very high level, the idea is that we create these various models, and these models have, say, a set of trainable parameters that we can alter and we can learn. And as we do that, we use these models to make predictions about data. And yeah, we then go and train these models so that we increasingly improve the accuracy of our predictions. So typical problems include things like classification. So say we have some input features. So machine learning, we use the word feature, but it's just like so if we have a two-dimensional vector where one dimension represents some type of data and another represents another type of data, we say this is a two-feature vector. So yeah, essentially each piece of data represents a feature. So in classification, this would be mapping features to, say, a binary. Is this, for example, credit card, is this fraudulent or is this genuine? Regression, similarly, and I also have some diagrams here. So yeah, this is, we have a 2D space, and now we're saying these are one class, these are another. Regression is more like, again, this is probably very familiar to you. This is mapping from input features to an output value. Say, I think of well-known ones are like you have the area of the floor space, or some location where you are in the city. So then you want to map all this to a house price, for example. Then there's things like clustering. So this is a type of unsupervised machine learning where we don't know if it's this class or this class, or we don't know if it's got a certain value for each data point. We instead say, okay, we just want to find out a way to group off different clusters of groups. So instead of this being such a classification, it would just be saying, okay, this looks like one group over here, and this looks like another group over here. And the final one is sampling.
Sorry, Tom. Sorry to interrupt you. Yves Verbelos here speaking. Just a short question. So clustering and classification are quite similar things. I mean, it's just the fact that one is supervised and the other one is unsupervised. Is that how you see it?
That's pretty much how I see it. They're very similar tasks. You just don't know. I mean, training practically happens quite differently. So instead of saying, so for classification, you say this is the input has this x coordinate, this y coordinate, and the output should be 0, and this one should be, the output should be 1, for example. Instead, you just don't know the output, and it's more like you're trying to fit in this two-dimensional space different regions. Okay. So I think that's more practically, the difference in training. And I guess it's typically a bit supervised machine learning. And so finally, there's also sampling. This is linked to some things like generative machine learning. And the idea is that we say, actually, we want to generate this data set. So instead of being supplied a data set that we just want to learn, we say, okay, let's have a reference data set. We're going to train a sampler so that we can reproduce data that kind of looks like it. So in this case, it would be, we'd make a sampler that sometimes generates points in this cluster and sometimes generates over here. So this is just a bit of a high-level introduction to the typical problems we have in machine learning. Now we want to have a look at deep learning. So this is a bit of a subfield. It really focused on neural networks. So yeah, here I say in 10 words, the idea is just to build models out of a series of composable and differentiable functions. So over here we have just an example of a neural network where this is a feed-forward neural network, so we line up layers of neurons. So you can imagine some input data comes in here. This is then passed on to a second layer. And by passed on, I mean this layer is effectively applying a matrix multiplication. So this is kind of a vector, right? This is applying a matrix multiplication to this vector. So we apply a matrix multiplication to this vector. It can change the dimension. And we can also add a bias. So that's this one here. And then finally, we can apply a nonlinear function. So something like, I mean, it could be something like sine. It could be anything really. But we typically do slightly more exotic ones like a ReLU. So this is called rectified linear units, where anything below 0 gets mapped to 0. So -1 goes to 0, for example. And anything above 0 just is left the same. So in long story cut short, the idea is that we've applied a series of differentiable functions, a matrix multiplication, adding a bias vector, and doing this application of the nonlinear function. So yeah, this is really how we think of the deep learning workflow. We have some function. It's really like an input-output relation. We have some input data here and some trainable parameters. Here we've written it, so this is this nonlinear function, matrix multiplication, and the bias. Could be something else, but the idea is that this is a differentiable function. So this is actually showing just one layer of the neural network, but we can actually compose a couple of layers together, for example. And with this f defined, we can then go on to look at a cost function. So we say, okay, we input a data point x into our function, and we get out some sort of y tilde or y primed, where this is our prediction. And what we want to do is to train this to be as close as this. This is the actual y, the training y. So yeah, take this difference and minimize the difference. So this is effectively the mean squared error that we're minimizing here in the cost function. So now we've defined a cost function. How can we minimize this? So this means how can we choose these thetas to get C to be as small as possible? And there are many ways to do it. The canonical way in machine learning is to use gradient-based optimizers. So we have, yeah, I mean, I think this is all fairly elementary stuff. We have a series of iterations of this gradient descent optimizer where the parameters are updated in each step. So what we do is we use the parameters from the previous time step and then just make a tweak where we sort of walk downhill in the direction of the gradient. Here eta is the learning rate, or essentially how much of a step you take. So this is the workflow for deep learning. Once we've trained it, we can use the model for classification, for prediction, as we discussed on the first slide. Now, how is this successful? Even up to, say, I don't know, 10, 20 years ago, it was very hard to train these deep neural networks. We just didn't have the underlying hardware to train successfully. It was so I think, for example, here it's still a fairly simple neural network, but you can imagine if we scale up this width or we scale up the depth, things can get a bit tough to simulate on hardware. But over the last 10 or so years, GPUs, as you can see here, have really come into play, and these things are really suited to these basic linear algebra sort of routines. So this is why deep learning has become successful, I guess, over the last few years. We've just made some hardware advancements. We also rely on some typical workhorse algorithms. So this is things like using gradient descent for the optimizer. Also, how we differentiate the output of the neural network with respect to its parameters. So we have some output. We might want to differentiate this with respect to some parameters over here. How we do that is using backpropagation. So we sort of pass. So when you evaluate a neural network, you do a forward pass. So you have some input, you go through here, and you get some output. We then have this backpropagation algorithm that lets us evaluate the derivative of this output with respect to certain parameters here. And we do this by stepping back and using applications of the chain rule. So there's like as I was saying, there's a good set of algorithms, workhorse algorithms that we use. But then also, of course, we need the software and the ability to sort of program these things up freely in a user-friendly way. So what sort of software is available out there? There's TensorFlow, PyTorch. These are probably the two famous ones. There's also a variety of other ones available. All what these software packages do is they let you compose these functions and differentiate their output with respect to certain parameters in there that compose the functions. So I'm now going to talk about quantum machine learning and contrast that with machine learning. Is there any questions for now? Okay, onwards. So I believe this slide is probably a bit low level for the audience, but there's, of course, quantum computing. So this is like a slightly different model of compared to classical computing. We have these quantum gates, quantum states coming in, have some processing, and then we have some measurement at the output. And really, as I'm sure you know, the power of quantum computing comes from things like the ability to interfere these complex amplitudes, so superposition, and things like entanglement as well. And then in terms of constructing the quantum circuit, so we do often think of having some input state, psi, pretty much always, even in quantum machine learning, this is just 0, 0, 0. But the interesting part for the QML perspective is this unitary transform U of theta. So we have some series of gates. These gates can depend on some parameters theta. And so this overall realizes a unitary U of theta, and the theta is the thing that we have access to train, to change the thetas and then influence the output of our circuit. So typically, of course, we have to measure some accessible quantity from the quantum circuit. So we have some observable, for example, B, so measure the expectation value. So when we think about this expectation value, we write it down using Born rule. It's fairly simple. We have this. So this is really just a series of matrix and vector multiplications. It's actually, although it can be exponentially big to write down, what we're actually doing is fairly simple, just matrix vector multiplication. So it's just linear algebra, and when you look at it, you can see that the expectation value depends continuously on these gate parameters. So this means that we can think about differentiating the quantum circuit. So this leads to this idea of quantum deep learning. So beforehand, we were saying in deep learning, we can kind of train neural networks. Now for quantum deep learning, let's think about, instead of a neural network here, let's replace this with a quantum circuit and train that. So we have some input, we have some trainable parameters to our quantum circuit and some output expectation value, say. Just like a neural network, maybe the contents inside are a bit different. But let's see what we can do in terms of training. So why would we want to do that? I guess there's two perspectives that we often think. So one perspective is this quantum for machine learning. So the idea is we use these quantum neural networks, these trainable quantum circuits, and apply them to standard machine learning problems. So things like we have an image and we chose a cat, I guess, for quantum, but we have some image data coming in. We feed it onto, so we embed this into a quantum circuit, train it just like a neural network, and then we classify, is it a cat or not? So this is the perspective of using quantum for machine learning. We often think, as I said up here, we often think of the quantum device probably isn't going to be a replacement for every part of a classical computer. It's more like, at least in the near term, going to be a special purpose device, like a complement to a GPU. So maybe a GPU is suited to neural networks, and then you could use a QPU for training these quantum networks. So then the flip side is this idea of actually training the circuit, the quantum circuit, to say learn new things from quantum, maybe to learn, optimize an algorithm, or to maybe fit new laws of physics, or even maybe find new physical laws. So this is really going on the idea that, okay, so we can train these quantum circuits, and quantum computers, quantum circuits are a very natural thing to simulate quantum systems, like in, say, quantum chemistry, molecules, for example. So it seems very fitting to use these systems, and actually it's one of the focuses in QML to is this so-called VQE algorithm to find the ground state energy of a molecule that you've encoded into this quantum circuit. So I'll talk about that later on in the talk. So yeah, comparing, we had a similar slide. How was deep learning successful? So how can quantum machine learning be successful? So we again need these hardware advancements. So in comparing to the GPUs from before, we need to build up these to have quantum to essentially freely define our quantum circuits and then train them on hardware. We need to build up workhorse algorithms, so things like how do we access the derivative of these circuits, how do we train them, and of course we need the supporting software. So beforehand, for deep learning, we have things like TensorFlow, but that doesn't, of course, cover training a quantum circuit. So we need software on that side. This is where PennyLane, as one of them, comes in. There are some cool other ones, like TensorFlow also has a quantum package. That's interesting. Then there's this Tequila package as well. So yeah, they're all cool to check out. Obviously, I'm biased to PennyLane. I think it's good. And I'll mention a bit later in the talk about PennyLane. So any questions, any more questions so far? Cool. So I spoke about how we have this quantum circuit and it's got a well-defined derivative. So we've got some expectation value coming out, and we can, its derivative is defined. But how do we actually access this derivative? So one option maybe would be to do it on a classical simulator. So we simulate our circuit, and then we have the expectation value, and we also have the derivative in simulation. But when we do that, we can see this just isn't going to scale well, right? So if we have a lot of qubits, so we increase the depth, this is just intractable on a classical simulator. So it's a bit of a question. How do we, although it might be defined, how do we access the derivative of this circuit? So there's a couple of ways you could think about it. I guess maybe the brute force way would be to use finite differences. So we have the circuit where we've got its expectation value. What we can do is calculate the expectation value, then shift the parameter that we're interested in, shift it by a tiny amount, calculate the expectation value again, and use the finite difference rule. So this is one option. I guess it often seen as a fallback option for us. Another thing we could do, as I mentioned, is we could do it all on a simulator or classically, but it just doesn't scale well. So maybe if we didn't want to do either of these, we could think about, okay, maybe let's not even bother with accessing the derivative, accessing the gradient. Maybe we could just pick gradient-free optimizers, for example. And this has been considered in quantum machine learning, but I think there's a reason that in machine learning, gradient-based optimizers are really the gold standard. And yeah, I think we should be expecting to use gradient-based optimizers in quantum machine learning as well. So how do we get practically this derivative? So let's take a step back a second and just think about this very simple problem. So suppose we have this function f of theta is sine theta. And suppose we want to differentiate it. And of course, we all know that the derivative is cos theta, but suppose we didn't know anything about calculus. And all we're told is that we can query this function. So we can evaluate this function for any value of theta, and we want to evaluate the derivative of this function. So because it's sinusoidal, we can use trigonometric identities to show this. And what this says is that the derivative of the function can be found by querying the function itself twice. So what we do is we query the function at theta plus pi over 2, and theta, so like a forward shift, and theta minus pi over 2, so a backward shift. Calculate the difference and divide by something, and yeah, now we get, so this is the derivative of sine theta, without knowing anything about cosine of theta, for example. And actually, this is something we call the parameter shift strategy. We, not just Xanadu, but the sort of quantum machine learning community. So yeah, here it's essentially the equation shown again with now an arbitrary shift. So before we had pi over 2, now we just have a shift of s, and this c also depends on s. So this is the parameter shift strategy, and it really holds for these classes of functions that are trigonometric based. So why is that interesting to us? Well, when you think about it, when we define these quantum circuits, often the gate with the trainable parameters is often just a rotation, a single qubit rotation. So an Rx rotation or an Ry rotation or some combination thereof. And these are actually pretty simple gates. And when you think about it, it's based on have kind of strong links to trigonometric identities. So this means that we can effectively use these circuits that are composed of only these rotation gates. We can evaluate the derivative of the circuit, the expectation value. We can evaluate its derivative with respect to those sort of gates by using this parameter shift rule. So this is a really cool thing. It's an exact estimation of the derivative. So bear in mind that the finite difference rule is always an approximation, right? This gives you the derivative exactly. So yeah, this leads to this at the slide that's really to emphasize that this is not finite difference. So it looks really close. Actually, one of the things we would struggle with in terms of sort of getting the point across is that it is different. So yeah, in both cases, we have the function evaluated at a forward and backward shift, and we're taking a difference. But for finite difference, this delta theta, this is ideally infinitesimal, right? You want this to be as small as possible. Whereas in the parameter shift rule, we actually showed you with a shift of pi over 2. We have some freedom on what the shift is. And also this, I guess is maybe a bit hidden on this slide, but this denominator, this c, well, actually, it's kind of often written as a denominator here with 2 sine of s on the bottom. So there's a bit of a difference there as well. And yeah, as I mentioned, so this makes the parameter shift rule exact, whereas the finite difference estimator is an approximation. Yeah, so another thing we mentioned here is that when you when you, yeah, actually, I think we talk about this more in the following slide, probably better explained here. So beforehand, I was talking mainly about, say you have a noise-free device, you have like a perfect access to this expectation value without having to sample it from an actual quantum circuit. So kind of in the ideal case. But suppose we're not in the ideal case now. We've actually got a real quantum circuit. It's got noisy gates, and we estimate an expectation value with a limited number of shots. So I know we typically use, say, 1,000 shots to estimate the expectation value. When we do that, we can then see we've got a finite difference estimator, and we've got a parameter shift estimator, and we can think about how they compare. So for finite difference, actually this estimator is biased. So the finite difference estimator is biased of the derivative. And also you can imagine that we've got to have these fairly small shifts. Otherwise, we've got a large bias. But when we have these fairly small shifts, and so on an imperfect device, we actually have this distribution over values of this expectation value. And this distribution kind of washes out our ability to resolve these tiny differences in the function. So these shifts should be small, which means that we expect these two quantities to be fairly small. And that really just gets washed out when we have a finite number of shots. Whereas with the parameter shift rule, we can have a large shift. So this can be, instead of 0.00 whatever, this can be pi/2, for example. So there's a lot of merits to this parameter shift rule. It's exact in theory. It's an unbiased estimator in practice when you're estimating the expectation value. When can we actually use it? We can use it, okay, on simulators, but the cool part is that we can use it on hardware. So we're really just querying the hardware, say, twice for a forward and backward shift of the parameter. So I did allude to this a little bit. Not all gates have this parameter shift recipe. Most of them that do. So any gate that is generated, so you have e to the IHT, for example, where h, so it's generated by h, and for any h that is involuntary, so self-inverse, we have this parameter shift rule. So this happens to include, typical single qubit rotations, for example. Otherwise, I actually don't have a good example of a gate that doesn't have the parameter shift rule. But in certain cases, if we don't have access to it, then we can just fall back to this finite difference approach. But really, we should be, as the default, trying to evaluate the parameter shift derivative. So this slide is, going back to this idea that in theory, expectation value, then the parameter shift derivative is exact. But of course, we have noise from devices. We have statistical noise from estimating the expectation value. So I think I've already mentioned this already. This is another cool point of the parameter shift rule, is that it's unbiased relative to the finite difference rule, which is biased. So now we can put the pieces together. So we know we have this idea over here of training a quantum circuit. So we have some input data and some theta. All we wanted to do was get this derivative so we can train using gradient-based optimizers. And now we can do it using this parameter shift rule. So we've kind of brought together the two pieces that we need for training quantum circuits. Any questions? Cool.
Well, I had one. Can you go back to the slide where you were comparing the just maybe I'll tell you when.
Before this section?
No, it was after. Yeah, the slide, like there were two columns.
Oh yeah,
here. So
okay.
Yeah, so if we think back of, you're saying that you can fall back to a finite difference estimator when the parameter shift rule cannot be applied.
Yeah.
I mean, I guess we can. There can be cases where just that is intractable as well. No. So isn't that a big caveat?
I think you can always evaluate the finite difference rule on hardware, even well the parameter shift. Say, let's get our device, let's evaluate it with a forward shift, with a backward shift and divide. So I think this is always possible, but the difficulty there will be, so it's always possible, but the difficulty in that these two differences will be quite washed out. So there's going to be this huge statistical noise that over this difference. So I think that's more of like a practical constraint on using the finite difference as a fallback, but it is in principle possible. Yeah.
And there's no way maybe to improve on this washing out, or like.
I mean, I guess there's a lot of theory on improving like numerical differentiation. So I wouldn't be surprised if you know, if I remember correctly, you can take like 4 terms, right? I think.
Yeah.
Get a better derivative. So I think maybe, yeah, I'm not sure. Probably we look mostly at parameter shift. I think there's probably scope for improving the finite difference estimator, maybe using it a slightly different method. But we've often just, it's just so often that parameter shift is the way that we can evaluate the derivative that I mean, I don't really know when we've had to fall back, to be honest, because so many circuits that we design and think about are just with these rotations. So really parameter shift just becomes the focus, and it's also handy that that's the best approach as well.
Yeah. It's a neat idea. Okay.
Yeah.
Okay. Thank you.
Thanks.
So sorry for the noise. I dropped my.
No worries. Okay, so we've talked about how we can evaluate the derivative of these circuits, but what should these, you know, how should we actually compose these circuits? What should they look like? So this comes to this idea of variational quantum circuits, and we've already really touched on it, but I just wanted to formalize what the idea is. So the point is that we restrict the circuit layout, the architecture itself. So we fix the gate. So we say, okay, this qubit has to have this gate applied here, then we have this gate. So we've got a fixed layout, but what we can do is the gates that do depend on parameters, we can try and vary them and train them. So this is actually very suited to near-term devices. So instead of saying, okay, we don't really know what our circuit is going to look like, we want to have freedom on where we place the gates. We say, okay, gates are fixed. Let's train the parameters. Yeah, so this is suited to near-term devices. You can imagine where you might have a fixed architecture, for example. You might have restrictions on the connectivity between qubits. So you can kind of hard code that connectivity restriction into your variational circuit and then train it. So this idea of variational quantum circuits really came out of 2 algorithms, but I'll talk about a bit later, QE and QAOA algorithm. So I'll talk about it in these next few slides, actually. So going one step above a variational quantum circuit, we can actually talk about the algorithm. And you can see at this point, it's starting to look a lot like machine learning language. So we have our Ansatz, which would be, I guess, the equivalent of a neural network. We define our cost function on top of it. In this case, I guess we've got a couple of circuits. We're evaluating different expectation values and summing them together. So we've got some sort of composition of our quantum circuits. And then we have this training procedure. So we have this cost function and we update the parameters. So this is just to formalize that it's in the end, you compose it in a very similar way to how machine learning and deep learning look. So now one example to look at is this VQE, variational quantum eigensolver. This really has its roots in chemistry. So you imagine we want to do some electronic structure calculations. For example, we have this molecule and we want to find, say, the ground state and the ground state energy of this molecule. How can we do this? So the idea is that there's some Hamiltonian that describes the system. What we can do is this Hamiltonian can be converted into a qubit-based Hamiltonian. This is there's a couple of transforms you can do. You can do a Jordan-Wigner transform. There's some others as well. So now we convert this molecule into a qubit Hamiltonian. And what we want to do is we want to find the ground state and the ground state energy. This means that we then want to minimize the expectation value of this Hamiltonian on our qubit circuit. So in terms of this variational approach, what we do is we come up with a circuit ansatz. So we say, let's arrange our gates in this certain way. How we arrange our gates, I'll talk about a little bit later, but for example, there's one way where we can do a kind of chemistry, quantum chemistry inspired approach. So once we have our ansatz, we then move on to this cost function. So as I mentioned, we want the ground state energy of this. So that's minimizing the expectation value of this qubit Hamiltonian. So once we've set that up, it's just a case of training. So we have our circuit, we measure a couple of expectation values on it, and we want to minimize this. So we say we can use gradient descent, that optimizer, for example, and we need the derivatives, so let's use the parameter shift rule. And this is just one plot that we showed. Actually, it's not even a plot, right? It's a nice diagram. But yeah, we get these sort of plots using when we look at penny lane, for example. So, okay, another algorithm is this quantum approximate optimization algorithm. And here, one example problem that this might solve, there's lots of graph-based, also icing problems that QAOA is used for. This problem is looking at max cut in this diagram. So the idea is we have some graph with some connectivity, and we want to find a way to partition the nodes of the graph so that the cut, I guess the best way to say it is that the cut crosses the greatest number of edges. So this is max cut, and you can, this can be kind of rewritten in terms of a sort of icing sort of looking problem, which can also sort of be naturally encoded into a qubit Hamiltonian. So what we do in QAOA is to get this Hamiltonian, we call it the cost Hamiltonian, and we also define a mixer Hamiltonian as well. So the circuit Ansatz in QAOA, that's composed of, we do a small time evolution of the cost Hamiltonian, this unitary, and then the mixer unitary. And then we repeat that a couple of times, say 10 or so times. And the idea is that if you repeated this a long time, it would, I think it would, how can I say, yeah, it would sort of realize the time evolution of this unitary that we're trying to, sorry, this Hamiltonian that we're looking at. So, and once we've got our circuit Ansatz, we then want to define our cost function. And again, just like with VQE, we look at this cost Hamiltonian. So we've defined our cost Hamiltonian. We want to minimize this after being passed through the circuit. So just like before, we can use, we train this. We want to minimize this Hamiltonian. We can use gradient descent. Maybe we can use a different optimizer. Actually, here we're looking at this, suggesting to use this Rosalind optimizer. So going a little bit back towards the circuit Ansatz. So how do we choose? I mean, I guess it's pretty much just using assumptions, guesswork, to come up with some set of gates that compose our Ansatz. And then we try and minimize the Hamiltonian or whatever. We try and train our circuit, and then hope that we manage to come up with a good fit. But is it purely guesswork? There's a couple of motivations on how we can choose our Ansatz. So we might have some physical chemistry sort of motivation. So this would be this UCCSD circuit Ansatz that we saw for VQE. We might have the optimization problem might have a certain structure that suggests how our Ansatz should look like. So this is with QAOA, where we need to do these repeated layers of cost and mixer unitaries. We can maybe use some intuition from machine learning. But to be honest, it's often just a case of picking a typical nice circuit where you're trying to rotate all of the qubits, say, and then have some entanglement spread between all of the qubits. So yeah, often it's just a bit of a guess and hope that it works at this stage. I think it's still an open area of research on how you best pick these Ansatz. Of course, how you pick it is very important. So if you pick a smart Ansatz, then, well, I don't know about smart, but how you pick the Ansatz changes the range of functions that your model can fit. So you should be picking hopefully an Ansatz that can encompass the data that you're trying to learn on, or the chemistry problem that you're trying to do. So any more questions? Cool. I think I've still got a bit more time, so I will. So yes, the idea now is to talk about, okay, we can get the derivative of the circuit. We have some ideas on how we define our variational quantum circuit, like how we construct it in terms of gates. But then how do we then practically go on to train it? So when I talked about those two applications of QML, so using quantum quantum in terms of solving standard machine learning problems, of course, what we're going to have there is some input classical data coming in. So it might be a picture of a, we seem to be quite obsessed with cats, I guess, but yeah, it might be some classical data coming in. How do we then embed this data into our quantum variational circuit? So there's a couple of approaches to embedding. We show, these are actually from our Penny Lane documentation, but I'd say that the two obvious approaches are an amplitude-based embedding and an angle-based embedding. So this simple angle embedding is, you say, okay, in this case, maybe it's a 3-dimensional vector coming in. The first dimension, let's just encode this into a rotation on the first qubit. Second dimension is a rotation on the second qubit, etc. So that's like a very simple, maybe obvious approach of doing it. The other, maybe more quantum-inspired approach is, okay, we have 5 qubits here, so let's embed a 2 to the 5 dimensional vector into this system. So this is probably nicer in the sense that you get more data encoded into the qubits. The drawback of that is it's a much more complicated circuit to actually embed this data. So it's not just a rotation on each qubit, but it might have a fair amount of depth to realize that. And also sometimes we want to think about being able to differentiate with respect to the input of the circuit. And here it's a little bit harder to, because you've got so many gates, you have to be careful about how you decompose this into what sort of gates, and then keeping track of how to differentiate this. So these are two obvious approaches. There's some other ones actually we're showing here for, this is for a continuous variable system rather than qubits. So yeah, this slide is just to touch on, you do have to embed data, classical data, if you want to do quantum for machine learning. But we should also be careful about how we embed the data. So actually this slide is pretty hot off the press for some research from our team. So Maria Schuld, I think that you can't see because this, I think you can see, okay. So Maria Schuld is from our team. So this is a paper based on her results. So the idea is that if we use this basic angle sort of rotation-based embedding, you're pretty restricted on the class of functions that you can train. So if you just have one layer of embedding, then you can really do, I think it's just like sinusoidal functions. If you have, say, 3 embedding layers, so what I mean is this would be one layer that embeds the, I don't know, say 3-dimensional data, then this would be the same layer embedding the 3-dimensional data again, and then again. But if you do that and you then have these trainable elements here, then you get a bit more freedom, a bit more flexibility in your model. So as you increase the number of these layers, it's always a Fourier transform that a Fourier series that you're fitting. But the kind of complexity of this Fourier series increases with a number of these embedding layers. So yeah, it was just nice to share this slide in the sense that it's some nice new research and shows that we shouldn't just naively embed once using only this angle-based embedding. So now we know how to embed. The last thing is, what optimizer do we pick? And I've mentioned gradient descent as the optimizer. And this is probably the most sort of elementary, the first choice that you can do, which is just to update your parameters pointing down the slope. But in machine learning, so classical machine learning, there's a load of different optimizers that are inspired by the gradient descent optimizer. So some of them, this one's pretty famous, for example, and they often have access to not just the previous information about like the previous time step, but time steps before that. So then they can keep track of things like a momentum, for example. So yeah, here we see a nice plot of, you get slightly different results using different optimizers. But there's also, so these are using classical machine learning, but what about using quantum-based optimizers? Something that has, an optimizer that has access to information about the quantum system, for example. So here are the 3, and we talk about them more in this slide. So these 3 are built into Penny Lane, and the first one, yeah, we say it doesn't really use gradients. So what it does is it optimizes one dimension at a time, which I need to look into this one more because it seems a bit of a weird thing to say actually. it's somehow a bit of a cheat, but yeah, this is the, I guess, the summary, that it optimizes sort of along one parameter, then optimizes along another parameter, I guess going down. So then there's this quantum natural gradient. This is one of the ones that we worked on at Xanadu, on the theory side. So if you look at your optimization landscape, you might see that it's not sort of symmetric in terms of your parameters. It might be squashed in one dimension. So you might evaluate your derivative, your gradient here, and it's going to give you, okay, it'll say this is downhill. But that doesn't pay attention necessarily to this local topology of your optimization landscape. So you might end up overstepping in one direction, going a bit too far this way, then bouncing a bit too far that way. And you can imagine it just bounces its way, maybe bounces back around this minimum while struggling to actually sort of converge. So what the quantum natural gradient optimizer does is it effectively learns to stretch out. So instead of getting this squashed oval, we're getting this circular space now, so that we know when we make a step, we're doing it kind of fairly in all directions. And yeah, how it does this is it evaluates the Fubini study metric, and what this does is sort of rescales the gradient vector, so that it's yeah. So I guess one way you can think about it is either stretching the space or rescaling the vector here. And then finally, we've got a quantum system, and we have to get our expectation value by sampling, right? By using a limited number of shots. So there are some optimizers that think about, okay, maybe we want to use 100,000 shots overall. I guess the simple way would just be to use, let's say, always 1,000 shots for each expectation value. But what you could do is budget slightly differently and say, at the start, we'll use fewer shots. And then as we converge closer to the minimum, where it's a bit harder to, things get a bit more washed out, then we use more shots so that we maintain our sensitivity to the gradient. So there are these quantum aware optimizers, and yeah, I think that's pretty much it. How you then go on and train this quantum circuit. So, Carl, do I have time?
How much time do you need?
I could skip the hybrid part and just mention Penny Lane.
It's up to you. I mean, if it takes you about 10 to 15 minutes, I think it's fine.
Oh, sure. Yeah, I think I'm pretty sure I'll finish in 10 minutes. Okay. So yeah, this is definitely the last part before I mention Penny Lane briefly. So these hybrid models, the idea is that, okay, we can train classical computers. We now know how to train quantum computers. So why not just combine them? Why not have the best of both? So if we motivate this a bit, the idea is that classical computers are good at things. They're not bad. They're actually like the cutting edge technology used throughout the world, right? So they're very optimized, and we've got a lot of experience in using them, things like data storage, arithmetic, etc. But what quantum can do is, we probably don't expect it to replace that whole stack, but it could be used for its own sort of specialities. So maybe quantum is good at it has these superposition, entanglement, etc., which typically means that you can evaluate these hard to classically intractable functions. Practically, that might transpire to mean, say, a better quality of training in a machine learning model. So the idea is, let's build a hybrid where we can use the skills of both classical and quantum together, sort of divide the labor, as we say here. I think it's cutting off here. Okay, sorry, I think I must have copied over strangely. Okay, so variational circuits. I've talked about these already, but when you think about it, they're actually already kind of hybrid. The quantum part is, so the quantum circuit, it's giving us this expectation value and we're training, but there's a lot of classical processing going on. So it's getting these measurement statistics, thinking about using the gradient descent optimizer, how to update the parameters, then feeding it back to another evaluation of the quantum circuit. So it's already a kind of hybrid, but it's an inflexible hybrid in the sense that the classical part is fixed. So yeah, this picture is a bit limited. What if we then said, okay, let's make this classical part, let's make this trainable as well. So yeah, what happens if we do that? Then we can just compose classical and quantum elements together. So we might have a classical part quantum part, add it together, and we end up with a fairly rich, interesting hybrid model. I'd say it's still interesting to work out sort of like a research question on the best way to compose what's going to be an interesting hybrid model. But it's definitely a very interesting idea on putting these things together and seeing what you can do, I guess, with both of them together. So this leads to this idea of a computational graph. So this already happens in machine learning, where we just break down our set of operations into nodes of a graph. And really, so it's like a directed acyclic graph. And so we have this direction here. And really the idea is that these introducing quantum is just changing one of these nodes to be a quantum node. So I think I mentioned it here, actually. So we have these quantum nodes. So really we're swapping out a matrix multiplication. This would now be a quantum node, where inside this, it would be putting in some data to a quantum circuit and evaluating the expectation value. And how this works is we have some input. So maybe we're using TensorFlow or PyTorch. It's got some input tensor coming in. In Penny Lane now, this would be transferred to the Q node, evaluated, and then fed back to like the rest of the computational graph. So now I will mention Penny Lane, even though I've sort of alluded to it a lot. So here we say Penny Lane, it's open source, so feel free to check it out, even contribute. We love contribution, Python based, and we call it a differentiable quantum programming package for near-term devices as well. Basically, I'd say everything that I've just discussed for the last 45 minutes, it can do that. That's the summary, I guess. So one of the cool features I just wanted to mention was that it allows you a lot of freedom with your machine learning framework and the underlying hardware, the quantum backend that you want to use. So you can use PyTorch, TensorFlow, or NumPy. So these are different like differentiation libraries. Actually, this is AutoGrad underneath if you're interested. You can use Penny Lane, and underneath you can evaluate on quantum simulator or hardware. But you can choose, so you can use Circ simulators, or you can run on Qiskit hardware, for example. Strawberry Fields, which is our photonic package. So yeah, this will be the last thing if I've still got time. This is just a quick qubit rotation demo. So it's kind of the hello world of Penny Lane, of QML in Penny Lane. So the idea is that we have a qubit. We start off maybe in the 0 state, and we want to train to get to the 1 state. And our variational circuit is an X rotation followed by a Y rotation. So of course, we all know that this could be done fairly easily with just a rotation that I think is pi over 2 on X and nothing on Y. So this could be done, but can we train it to do it? So in Penny Lane, so this is now some Python code. We import Penny Lane, we load our device. So now we're using a Rigetti Forest QPU. So this would actually be hardware, but you'd need to access, if you wanted to try this at home, you'd need to sort of use your own access token. So then we create our Q node. So this is a very simple circuit. We have the X and Y rotation, the expectation value is the output. And the rest is just classical optimization. It's just like the rest of the computational graph. So we define our cost function. We want to minimize the expectation value to be as close. So we want the expectation value to be as close to -1 as possible. So we have this squared error sort of approach, and we want to minimize this. We have some trainable parameters, and we just run the optimization loop. This is showing where we're actually changing the target from 0 state to 1 state in time. And last slide, how do I learn more? Well, I think the best place to check it out, obviously, is pennylane.ai. So we've got a load of tutorials for you to check out. And it's not just necessarily sort of Python focused. It also could be used for like picking up general knowledge, general theory about quantum machine learning, for example. And this is what you'll be greeted with if you go to that website. So yeah, happy to open up for any questions, any comments, and thanks a lot for listening.
Yeah, thank you very much, Tom. Very insightful talk. Yeah, I learned a lot myself. So, all right, any questions?
So maybe I have one. It's Yves Rubelosier speaking.
Hello.
Hi, it's again me. Well, so you've talked a lot about Penny Lane. Well, the stuff that is more software oriented, and how is that going to interact with the hardware that Xanadu is developing? So, do you expect that you will be able to run all of this on your hardware, or so? How was the strategy?
So, I'd say really the interface is this this kind of cheesy looking jigsaw, where what you can do is you can pick your device. So you can pick simulators, whatever, from different providers. But here we have the Strawberry Fields. So it's this Strawberry Fields package. It gives you a set of devices. One of them is photonic simulators.
Yeah.
But also, it's still fairly recent. I think over the last few months. But we also have like a hardware access now, so you can use with the hardware as the underlying sort of back end. You can then evaluate, say, the derivative of the number of photons in one mode with respect to, like, say one of the beam splitter parameters, for example. So that elementary part is there. And then I think it's just a case of, I say, waiting for some progress on the hardware side. So we want to have things like trainable squeezers, for example, rather than on-off squeezers. But yeah, I think it's pretty much there. It's just a case of scaling up the number of modes, working on losses, sort of hardware side problems. On the software side problems, a lot of the well, maybe not software, but theory side problems, a lot of people still talk about variational qubit-based quantum circuits, whereas variational photonic-based quantum, CV-based quantum circuits is still a bit new. So I think that's probably where there's some questions on, you know, what can you do with these? Do they give you any advantage over qubits, for example?
Okay. Well, and just as a comment, your presentation was extremely good. I really enjoyed it. I also learned a lot myself. So thanks for having taken time to come to us.
Yeah, it was a pleasure. Thanks very much.
Yeah.
All right, thank you, Yves. I see that Marc-Antoine has a raised hand. Do you want to go?
Yes, just a quick question. You showed us how to optimize to get, for example, like the Hello World example, just a simple rotation. But can we expand that concept to maybe you have a complex gate or a complex circuit? Can we use optimization to maybe do error correction in some sense?
So certainly I had a backup slide here where there's it's actually a bit hidden, but this is a slightly more complicated circuit where we're embedding data fairly simply, but here we're using a template from Penny Lane. And this template is these basic entangler layers are pretty much more complicated. So it's like a series of single qubit rotations, then a series of C0 gates, which are then repeated. So certainly the circuit itself can be made much more complicated, either by manually placing the gates with like RX, for example, and C0s, or by using these templates. And then in terms of like the problem space, I think it's an interesting question to look in terms of error correction. I've looked for a couple of projects at error mitigation, and it's kind of interesting. One thing practically on the Penny Lane side is that we're only just introducing noisy mixed state simulators. So that was a bit of a hold up for like simulating with noise, with errors. But certainly if you've got access to like IBM, you can evaluate on the like noisy hardware and see how error mitigation or error correction would work. Yeah, I think it's an interesting project.
All right, thank you.
Max, I see your hand. Do you want to go?
Yeah, thanks for the very nice talk. Maybe I missed it. So can you tell a bit more about the speed up you can expect of quantum machine learning with respect to classical?
So in most of this talk, I've focused on these variational circuits. So I think this is very much the focus for the near-term quantum machine learning field. So because it's suited to this idea where you might have a fixed topology or a fixed set of gates that you can apply, and you can only train the parameters. And in that space, the question of speedups is a lot more murky. I think it's still, to get a speedup, I think that's still a research question to understand, like to put some hard, like computational complexity arguments on that. We have more rough statements on improved what we call representational capacity. So this is this idea that, okay, you've got a quantum device, so it should, it probably is able to represent functions that a classical device would struggle to replicate. And if you want to use that for machine learning, the idea might be that maybe you can fit better to a data set, or you can generate a wider, like you can sample better from a practical data set. So I think that's the status of sort of complexity in the near term. In the long term, there are all these, there's like a whole host of deep, requiring error correction sort of quantum algorithms that are applied to machine learning, where you do get these exponential or quadratic speedups. So there's the things like the HHL for matrix inversion algorithm can be used in machine learning. But then we go into this, you know, this, it's definitely long term, it's definitely deep, error corrected, a lot of buts, and it's a bit far away. So yeah, most of the time we at least focus on this near term approach.
Okay, yeah, very clear. Thank you. Just one more short question. So you mentioned this continuous variable approach. Does this parameter shift rules also apply to those, or?
Yeah, that's a very good question. It's a lot more complicated in the CV approach. So yeah, for qubits, you just have this pretty much this one shift. Okay. In CV, if you have all Gaussian gates, there is a parameter shift rule. It might be slightly different to the one that I showed, but there is a sort of, you do a forward and a backward shift sort of approach and divide by something. So it is there for Gaussian gates. For non-Gaussian, so maybe that's the good example actually. For non-Gaussian gates, we don't know of a parameter shift rule. Maybe there is, but it's still an open question. And that's the example where we fall back to finite difference. So if you want to do a cubic phase gate, for example, then in Penny Lane, we're using finite difference.
Okay, thanks.
Thanks.
Eddie, do you want to go?
Yeah, sure. Thank you very much for your talk. So I was wondering, when you talked about your quantum-inspired optimizer, I was wondering what is specific about the quantum optimization landscape that makes you think you can have a gain by using a quantum-inspired? Or
so this guy?
Yeah.
So it's actually interesting that this idea is, like, I guess, like so many quantum algorithms, this idea also happens in machine learning, where you might have a landscape that's kind of squashed in one direction classically as well. And there they're using the Fisher metric, if I remember correctly. Mm-hmm. So I think, so I also wasn't on this paper, but I think my understanding was that it was this idea that, okay, instead of the Fisher metric being the natural one for classical, like for a classical landscape, for a quantum landscape, we want to do this Fubini study metric. So yeah, I don't have a good intuition on then why the landscape might be quite different in a quantum model, but I mean, I guess I can say at least we've seen in practice that we get a speed up. So a speed up in terms of trading. So actually, it might take, you might have to, for each step, you might have to evaluate the expectation value more. But overall, when you count things up carefully, how many expectation values you've evaluated, it's typically fewer than if you were to use something like gradient descent. So I know that's not the best answer, but at least I know it works in practice, and I probably have to ask the team on more on the intuition side.
Excellent, thank you.
Jean-Frédéric, do you want to go?
Yes, thanks, Tom. I was wondering, you had one slide on the embedding of classical data, mm-hmm. and I was I was just curious if you could comment maybe on maybe some projects that are going on at Xanadu. What type of classical data are you interested in, and what's the size, typical size of this data? So, and where do you go this going in the next few years?
So I say some examples. Like I've personally worked on some CV-based approaches. So yeah, there we've looked at encoding things like images. So if you can imagine, you've got like a two-dimensional data set, right? And then we encode that into two modes of the quantum system. Each pixel going across is represented by an increasing Fock state up to a cutoff, and then this will be the other mode. So it's kind of like a matrix representation of the two mode CV state. That's one cool example I can give. It's often practically pretty tough. Even in that case, we have to have pretty high cutoff to get a nice resolution. It's pretty tough to get high dimensional data because the width of simulating, so when we're on a simulator at least, width is the hardest thing because this is the number of qubits. So if we go up to, I don't know, we can probably simulate 20 to 30 qubits, but to then evaluate the gradient, that's tough. So that means that we're pushing it if we're going up to, say, 20 to 30 dimensional data on simulator. Often in practice, what we do is we try and compress down as much as possible. So we have something like an encoder where, say, it's 100 dimensional data coming in, and we typically have our restriction and say, okay, we want to go up to 4 qubits. So it can be a pretty harsh encoding, but we can have a neural network. So this is harking to the sort of hybrid approach where we've got a neural network. It's taking us down to 4-dimensional data, and that 4-dimensional data goes on to then be embedded just like this. So yeah, I guess there's a mixture of approaches. Like in the near term, it's definitely tough to go for a high width. For amplitude embedding, this is also one that I think needs more work in terms of the decomposition. So how you actually, okay, you want to do these amplitudes, but how you actually break this down into elementary gates. Maybe on the Penny Lane side to program it up, and also to maybe think about more efficient decompositions as well. Did I answer all your question? I think I forgot the second part.
No, that's well. I was just second part was just where do you see it going in like next few years? But yeah, I think it answers the questions. Thank you.
Okay, thanks. Yeah, I think what we need is hardware really. That's going to be the cool part where we really start playing and we have a lot of fun once we've got a lot of qubits on hardware.
Thank you.
Maybe I have a last question myself, follow up on this embedding. Is it a step that requires a lot of computing resources, or is it simply just defining variables on the computer?
So I guess it depends on the embedding. This one I think is fairly simple. Like it's just saying it's directly putting each dimension into a rotation on the qubit. And also on hardware, I think that shouldn't be too hard because it's just a qubit rotation. So this one we've often used when we're doing like basic like example models on actual hardware. So we trained one on IBM, for example, where the data was encoded like this. Yeah, I think, yeah, I don't think there's a big classical overhead in embedding. It's all about like the decomposition and how you practically get that onto the device and whether that causes a lot of noise if you might end up with it with like a deep circuit, for example.
All right, thank you. So I don't see any other raised hands. Maybe a last call and questions. All right, so that's it. Thank you very much, Tom. Very good talk, and thank you for all the information today. Yeah, we appreciate it.
Thank you very much. Thanks for having me.
Thank you. Goodbye, everyone.
Bye. Thank you.